Hello guys, how are you today? So today I'll be explaining the chapter 6 course revision questions. So chapter 6 is about waves. We have 10 sections in total for chapter 6. So let us start with the first question. The first question says, differ between a pulse and a wave. A pulse, it is what? It is a disturbance that travels through a medium or space from one location to another. So remember, a pulse is a disturbance that travels through a medium or space from one location to another. Whereas a wave, it is what? It is a train of pulses. Very simply, that's CQD number 1, done. CQD number 2, is energy and matter transmitted from a wave? Energy is transmitted, so the energy will be moved by the wave, whereas matter is not moved by a wave. So energy is transmitted, but not matter. You can take the example of a rope, so you can move the rope up and down, and you could tie a string or a hair tie or whatever on the rope, and you will see that the rope will move and it will cause the vibrations and it will cause energy to travel, but the hair tie will not move its position. Okay, we move on to CQD number 3. It says define compression and rarefaction. Okay, compression is a region in longitudinal waves where the particles are closest together. So compression, we are discussing here in longitudinal waves. I don't know if I longitudinal waves. Please bear with me. I don't know if I wrote it correct. Longitude. Okay, wait, I wrote it wrong. Here we go. Oh my goodness, compression, it is longitudinal waves, okay, that are what? That are closest together, where particles are closest together, where particles are closest together. Whereas what? Whereas rarefaction is the rarefaction is the region in longitudinal waves. So again, it is longitudinal waves. Okay, where the particles are farthest apart. So where particles are farthest apart. Okay, so compression is longitudinal waves where particles are closest together, and rarefaction are longitudinal waves where particles are farthest apart. We move on to grid number 4. Define a progressive transverse wave. What is a progressive transverse wave? A transverse wave is a wave in which the particles of the medium move in a direction normal or perpendicular to the direction of propagation of the waves. Examples of transverse waves, we have water waves and electromagnetic waves. So water waves and electromagnetic waves. Okay, now we move on to part B. In part B, it says define a progressive longitudinal wave. What is a progressive longitudinal wave? A progressive longitudinal wave is a wave in which the particles of the medium move in a direction parallel. So they move parallel to the propagation of the wave. So transverse moves normal or perpendicular to the propagation of the wave, whereas longitudinal move parallel to the direction of propagation of the wave. Some examples, or one example, it is sound waves. Okay, another example of transverse waves would be the waves that move in the ropes. So as you can see, if you tie the hair tie, you will see that the hair tie will move up and down, not left and right, it will move up and down. So this means that it is normal or perpendicular. So that means the waves in the ropes, they are transverse waves. We move on to CQD number 5. It said describe the movement of air molecules and the pressure variation as a sound wave propagates through the air. So as a sound wave propagates through the air, it compresses the air molecules which relax as the wave advances. Regions of compression and rarefaction are formed where pressure is maximum in compression regions and minimum in rarefaction regions. So basically they are saying that as the wave is moving, okay, as the sound wave is moving, there will be some regions over here, like as it is moving, there will be some regions that is gonna be compressed, okay, and after the wave leaves that region, it will become then rarefacted. So as the wave is moving in the air, there will be some regions that are compressed, and after the wave leaves this specific place in the air, then it will be rarefacted. To what category of waves do sound and light belong? First of all, sound belongs to mechanical waves because it needs a medium to pass through. Mechanical waves, whereas the light is electromagnetic because it does not need a medium to pass through. So again, sound are mechanical waves because they need a medium to pass through, whereas light are electromagnetic waves because they do not need a medium to pass through. We move to question number 7. Sound is thought of as a train of pulses traveling in a medium. How is sound produced? Sound is produced, first of all, we know that sound is what? It is a mechanical wave because it needs to travel in a medium. So it's a mechanical disturbance because what's the definition of a wave? It is a disturbance. Okay, it is a mechanical disturbance. So sound is produced by a mechanical disturbance. Now, what do you expect sound waves in the air to be, transverse or longitudinal? They should be definitely longitudinal. They said, explain why you think it should be longitudinal. So definitely, if you take a candle, just remember the example of the candle. You light a candle and you start talking in front of this candle, you will notice that the candle will move back and forth, not up and down. So if it was to move up and down, then the wave of sound would be a transverse wave. But because the candle moves right and left, so it's moving with the waves of your sound, so that means it's moving along or parallel to the waves of the sound. That means it is longitudinal. Okay, they told us define sound waves. So if we are to ever define sound waves, how would we define them? Sound waves, they are defined as longitudinal mechanical waves. So longitudinal mechanical waves. First of all, they are longitudinal because this is their wave motion, because any object will move parallel to this wave, and they are called mechanical because they need a medium to pass through. We move on to section 6.3, the speed of propagation of a wave. Two cans connected by a rope can form a primitive interphone telephone. How can you explain that? We know that what's happening when you are talking in the can, you will have that the sound waves will vibrate, okay, through the can. So they will hit the walls of the can and they will vibrate back and forth. Now this vibration will pass through the string, okay, and the string will move back and forth. So it will move the string, these vibrations. So then the bottom of the second can will start to vibrate back and forth because of the spring, and you will be able to hear what? You will be able to hear the same sound as that in the first can. So again, you have the can over here, and then you have the rope. It's connected to then another can. Okay? So what's happening is that when this is a person, let us say, cannot draw person, this is the nose, this is the mouth, okay? Oh my goodness, this is the nose of the person and this is the mouth. Now the person is gonna be talking, okay? These are the sound waves. The sound waves will start to move back and forth. They will bounce everywhere and they will cause what? A vibration. This vibration will then cause the rope to move, so it will cause like vibration in the rope. It will be moving in the rope. And then this will cause what? Another vibration in the can, exactly the same as this one over here. And it will be able to be heard by this person over here. So this is the person's ear, and it will be able to be heard by the other person. Now, give me a second, I want to drink some water. Okay, my apologies for that. Let us move on to CQD number 10. A train of waves travels in a stretched spring at the rate of 2 waves per second. They want us to find the period. We know what? That the period, it is the inverse of what? Of the frequency. Okay? So they told us that a train of waves travels in a stretched spring of 2 waves per second. So they gave us the frequency to be 2 waves per second. So 2 hertz is the frequency. So to find the period, which is how long it takes one wave to move, it is gonna be 1 over the frequency. So 1 over 2, and it will give us an answer of 0.5 seconds. Okay? We now move on to part B. They said the time for one complete cycle of a musical note is 4 times 10 to the power of minus 3 seconds. Find the frequency of the sound. So we have what? We have one complete cycle, or one wave, being this many seconds. So this is the period. Okay? They said find the frequency of the sound. The frequency of the sound, it's gonna be 1 over the period. So it's gonna be 1 over 4 times 10 to the power of minus 3. Let's put it together. 1 over 4 times 10 to the power of minus 3. We will get that the frequency is equal to 250 hertz. We move on to part C. We know that in part C, a radio station broadcasts at a frequency of 100 megahertz. Find the period of this electromagnetic wave. Then it's going to be 1 over 100 megahertz, which is 100 times 10 to the power of 6. Put it on the calculator. 1 over 100 times 10 to the power of 6. You will get that the period, okay, it is then 1 times 10 to the power of minus 8. So that is it for CQD number 10. We'll move on to CQD number 11. Draw and label a displacement position graph of the particles along the wave train at a single moment. So let us say, okay, this is over here. Displacement of particle A. We're doing number 11, by the way. And then over here, this is the position along the wave train. So what's gonna happen is that you're gonna have the high and the low, and the high and the low. And so anyways, they want what? They want us to draw and label a displacement position graph along the wave train at a single moment. So this is the displacement position graph of the wave train. If you want to find the wavelength, lambda, it's gonna be from crest to crest, or from 0, skip this one, so this one over here, or from trough to trough, but there's no trough, so you can take only these two. We move on to question number 12. In question number 12, they said what? They said draw and label a displacement time graph of a single particle in the wave. It's gonna be literally the same exact thing, but here we are gonna be dealing with a single particle and not the particles. A single particle. So look what's gonna happen. It's gonna be over here, the displacement of particle A, of particle A. We're gonna draw this over here. We're gonna have the time, and you're just gonna draw the graph. The graph will look like this. Let's say, for example. Now from here to here, this is gonna be what? This is gonna be the period, because we are discussing of one particle, so it is the period. Very simply, I think that is it. CQD number 11 and 12, I don't think they're coming, so don't pay too much attention to them. Anyways, we move on to CQD number 13. They said define frequency, wavelength, amplitude, and wave speed. First of all, what is frequency? Frequency is the number of cycles completed per second. So you can write frequency, number of cycles completed per second. That is it for frequency. For wavelength, what is the meaning of wavelength? Wavelength is the length of a wave from one peak to the next. Okay? So the wavelength is the length of a wave from one peak to the next. After wavelength, we have the amplitude. The amplitude is the maximum displacement of a particle from its rest position. So the maximum displacement of a particle from its rest position. And then finally, the wave speed. The wave speed is the distance traveled over time. Very simply, you can say distance over time. Now we move on to 14 grid. In 14 grid, they said, what is the speed of a wave of frequency 4 times 10 to the power of 14 hertz and wavelength in nanometer, 750 nanometer. So look what you should know. You should know that the speed is equal to the frequency times the wavelength lambda. So the speed, which in this case we need to find, you can denote it as S or V. It is equal to 4 times 10 to the power of 14 hertz. And you're going to multiply it by the wavelength, which is 750 nanometer, which is 750 times 10 to the power of minus 9 meter. You're just going to multiply them together. And you will get an answer of 3 times 10 to the power of 8 meters per second. This is basically the speed of light. We move on to section number 65, so question number 15. Which sound travels faster, a loud sound or a quiet one? Actually, they both travel at the same speed. What happens is that the loud sound only has a higher amplitude than a quiet one. Okay, so the speed of propagation of sound does not depend on the amplitude. However, it only depends on the medium in which the sound is propagating. So if you have a loud sound, a very soft sound, or an intermediary sound, then they're gonna be all the same, which is the same speed, because they are passing through the same medium, which is air. Okay, both sounds travel at the same speed in the same medium. This is something very important to keep in mind. Now for part B, which sound travels faster, the one produced by a guitar or by a drum? They're both gonna have the same speed of sound, because again, both sounds travel at the same speed in the same medium, just as with a loud sound or with a quiet one. As long as it is in the same medium and we're dealing with the same type of wave, then it's gonna have the same exact speed. We move on to question number 16. In question number 16, they said wave A undergoes several changes to give waves W, X, Y, and Z. They said describe how the pitch of wave A changes in W and Z. In W, the pitch becomes much smaller because, as you can see, the frequency has become less. Whereas in Z, the pitch becomes much higher because the frequency has increased. Okay? Now, they want what? They want to describe how the loudness of wave A changes in X and Y. As you can see, first of all, in X, the amplitude is much higher, so that means X is louder, okay? Whereas Y, the amplitude is much lower, so that means that the Y has a lower sound, okay? We move on to 6.6, question number 17. Do different sound pulses pass through each other without change? How can you justify that? So, no, different sound pulses do not pass through each other without change. How can we justify that? Is that very simply, if we put two loudspeakers, okay, facing each other, and a microphone is allowed to move between them, then the microphone is going to detect some regions that have very high sounds, okay, and some regions that do not have sounds at all. So basically, they're saying that some of the sound will have destructive interference and some of the sound will have constructive interference. Do different light pulses pass through each other without change? How can you justify that? Again, no. Under certain conditions, they undergo interference. How we can justify that? Very simply, we can justify that by using maybe the idea of, if you bring two flashlights and you place them through a hole, then they will create one big hole. This I'm making it from the top of my mind. I'm just thinking of anything. So, like, let's say you have a flashlight over here, okay? And then you have this wall over here, and then the flashlight will enter through a hole. And then you have another flashlight next to it over here, and then you have another hole, and then this is the other flashlight, okay? And this is the light coming out of it. So, look what's gonna happen. What will happen is that the light that will pass here will go there, and the light that will pass here will go there, and together they will form what? They will form one big hole. I think this is one way you could explain that. Honestly, I'm not sure if I'm correct, so please do double check with ChatGPT or your teachers or whatever, okay? So we move on to question number 18. Draw two waves that interfere constructively and two waves that interfere destructively. So very simply, constructively, it would be like this. This is constructively, and destructively could be like this. So very simply, this is CQD number 18 done. We move on to number 19, which is 6.7, boundary behavior of a pulse wave. Does sound pass through and reflect from a barrier simultaneously? If you clap your hands 30 meters from the flat window of a building, can you hear the echo? Can people inside the building hear you clap as well? So yes, sound is transmitted and reflected at the same time. So remember that sound can be reflected and refracted at the same time. You will hear the echo of the clap, and the people inside the building will also hear you clap as well because of the reflection and the refraction. So you clap, it will reflect back to you, and it will refract into the glass for the people to hear as well. Now CQD number 20, they said draw the reflected pulse for each of the following scenarios: at a fixed end and at a free end. Okay? So over here at a fixed end, look what's gonna happen. You will draw the fixed end again. And we know that at the fixed end, what's gonna happen? We're gonna have an inversion, or like inversion. I don't know how to say it. It's gonna be inverted. There we go. So let me try my best to draw it properly. My bad. Like this, like this, like this. Okay, something like this, but it's gonna be inverted. This is the main idea we need to know, and the direction will be in the opposite direction. And over here, we will draw what? The free end, okay? It will not be inverted, it will stay the same direction. The same, not direction, the same, it will not be inverted basically, it will stay on the same side, but it will move in the opposite direction. So that's it for CQD number 20. We move on to CQD number 21, grid in chapter 6.8, waves in two dimensions. A plane wave strikes a straight reflector as shown below. Draw the reflection of the wave after the reflector. So look what you're gonna do here. You're gonna draw the normal line, okay? You're gonna continue this over here. Let me fix the normal line then. Okay? You're gonna continue this over here. It's gonna hit over here. So this is what? This is our angle of incidence, theta. And then it will be reflected with the same exact angle over here. So this is theta also. However, this is gonna be what? This is gonna be the ray of reflection. And do not forget to draw also the strikes, okay? So it's supposed to look something like this, all right? We now move on to CQD number 22. When a water wave travels from shallow water to deep water, it changes its direction. What phenomenon is being observed? This is first of all wave refraction. How do we know? Because it's going from shallow water to deep water. How does the speed and wavelength of the wave change? First of all, we know that the speed, when we are going from a shallower to a deeper, you should know that the speed will increase as well as the wavelength. So if we're going from shallow to deep, the speed increases and the wavelength increases, and also the amplitude increases. However, the frequency and the period remain the same. Keep this in mind. If we're going from deep to shallow, the speed, wavelength, and amplitude decrease, whereas the frequency and the period remain the same. We move on to CQD number 6.9. I think this is the last thing I will do, because the next one we have, like, I will go down. The next one we have is 6.11, and we do not have 6.11, okay? So, how does the interference pattern depend on the wavelength? First of all, the interference pattern depends on the wavelength because of the spacing between fringes. So, the spacing between fringes, okay, is directly proportional to what? To the wavelength. So interference pattern will depend on the wavelength. They're saying if this is the, first of all, like a stone and a stone, and you have the wavelength to be this small, no diffraction will happen, no interference will happen. However, if you have it big, then it's gonna be something like this. so diffraction will happen. CQD number 24, design an experiment using double slit to study the interference of light. So 24, to design the interference of light, look what we can do. We can place a cardboard with two small slits separated by a small distance in front of a screen. So this is our cardboard, it has two small slits separated from a distance in front of a screen. So this over here is our screen, okay? Then we are gonna shine a monochromatic laser. So we're gonna have a laser over here. We're gonna shine it from here. And you will see what? You will see a system of bright and dark, bright and dark, bright and dark, bright and dark. So here you will have what? You will have constructive interference when you see the light, destructive when you see the dark. So when you see the light, it's constructive interference. When you see the dark, it's destructive interference. Let's move on to 25 grid. Once a water wave reaches a narrow barrier, it spreads out after the barrier as shown below. What phenomenon is being described above? This is diffraction. As you can see over here, there is a small slit, the water is escaping and it is being diffracted. Now 26 grid. Michael sends a train of sound waves into a barrier. The waves leave the barrier, making the shapes shown below. How can Michael make the waves spread out more? Okay, after the barrier, list two ways. So he wants to make them more diffracted. He wants to make them like this. For Michael to be able to do this, he will need to what? He will need to reduce the size of, to reduce the gap, okay, of the barrier. So then it will be like this, and it will be more likely to diffract like this. Or he can increase the wavelength. So he can keep it the same distance, like this. But he can increase the wavelength. So now it's gonna be, then, at some point, like this. Very simply, that is it. So thank you guys for watching. We have 6.11 after. We don't have it, by the way. We have in chapter 6 from 6.1 to 6.10. Okay, so 6.11 we don't have it. Thank you guys for watching. I hope you enjoyed and have a wonderful day.